Okay, hey guys, so this is lesson 3, algebraic expressions. So in algebraic expressions, I would definitely highlight this, are just combinations of constants and variables using a typical operation of addition, subtraction, multiplication, and division along exponents and roots. So today we're going to talk a lot about square roots and a little bit of cube roots. So it's important to be able to evaluate algebraic expressions for values of the variables contained in them. So in our first example, it says, consider the algebraic expression 4x squared plus 1. Part A says, describe the operations occurring within this expression and the order in which they occur. So the first thing that we do, we notice that we're squaring x. The second thing that we're doing is we're multiplying by 4. And then last, we're adding 1. So those would be the 3 operations that we would do in this order, knowing that we squared first, then multiplied by 4 and added 1. Also think of order of operations. Exponents were dealing with the squared, multiplication was multiplying 4, and addition was adding the 1. So now let's go ahead and do part B. Evaluate this expression for the replacement value x equals -3. Show each step in your calculation and don't use a calculator. So we're going to let x equal -3 for our expression. So we'll have 4 times -3 squared plus 1. So 4 -3 times -3 gives us +9 plus 1. 9 times 4 gives us 36 plus 1 gives us 37. Okay, so let's look at exercise number 2. Consider the more complex algebraic expression known as a rational expression. So a rational expression is anything that you make into a fraction. So we have 4x plus 3 over x cubed minus 7. Part A says, without using a calculator, find the value of this expression when x equals 3. Reduce your answer to simplest terms. Show your steps. So everywhere I see a 3 or see an x, I'm going to plug in 3. So I'll have 4 times 3 plus 3 over 3 cubed minus 7. So I'm going to take care of the numerator. 4 times 3 gives me 12 plus 3. And my denominator, 3 cubed is 3 times 3, which is 9, times 3, which is 27, minus 7. Then I'll add the numerator, 12 plus 3 gives me 15, and 27 minus 7 gives me 20. Well, they want us to simplify it even more, so I need to reduce this fraction of 15 over 20, which I know both of these can be divided by 5 and come out evenly to help me reduce my fraction. So 15 divided by 3 gives me 3, and 15 divided by 5 gives me 3, and 20 divided by 5 gives me 4. Notice here we crossed out letter B, so go ahead and cross out B. Okay, expressions can contain more complex operations, such as the square and cube roots, as well as absolute values. We will need each of these over the span of this course, so some practice with all of them is warranted. Exercise number 3 says, is the absolute value expression of x minus 8, the absolute value of that, plus 2, equivalent to the absolute value of x plus 10? How can we check this? Well, we know that this word here that says equivalent simply means that we have to have the same value for every x. So wherever we have x and set it equal to the new equation, those values, x could be the same, but those values have to also equal each other later on. So we're going to test some points. So let's go ahead and test. What if we let x equal -5? Let's try -5. If I plug in for the value, remember the absolute value of -5 minus 8 plus 2, and set that equal to the absolute value of -5 plus 10, let's see if these values will equal each other. So -5 minus 8 gives me the absolute value of -13 plus 2 equals the absolute value of -5 is 5 plus 10. The absolute value of -13 is positive 13 plus 2 equals 5 plus 10. Well, 13 plus 2 gives me 15, and 5 plus 10 gives me 15. So yeah, that worked. But every time you want to check values that deal with an absolute value, we also want to check another number just to verify that those two expressions are equal. So what if I try to test out letting x equal +5? So if I let x equal +5, what happens? I have the absolute value of 5 minus 8 plus 2 equals the absolute value of 5 plus 10. Well, 5 minus 8 gives me the absolute value of -3 plus 2, and that equals 5 plus 10. The absolute value of -3 is 3 plus 2 equals 15. Well, 3 plus 2 is 5. 5 does not equal 15. So in fact, these two expressions are not equivalent to each other. So it's always good to check to make sure if these two values are equivalent. So we say they are not equivalent. Because any value that I let x equal, it should be balanced on both sides no matter what I let x equal. Okay, example 4, or exercise number 4. Consider the algebraic expression, the square root of 25 minus x squared, which contains a square root. Part A says evaluate this expression for x equals -3. So take a few minutes to see and try this. So we have the square root of 25 minus -3 squared. So the square root of 25 minus, well, -3 times -3 gives me a +9. So 25 minus 9 gives me the square root of 16, and the square root of 16 is 4. Let's try part B. Why can you not evaluate the expression for x equals 13? Take a minute to see if you can figure this out. So let's go ahead and plug 13 and see what happens. At the square root of 25 minus 13 squared, we get 25 minus 169. Oh, I notice here that 25 is bigger than 169. It's going to give me a negative. So I get the square root of -144. I never want a negative underneath my radical. So this tells me that I cannot evaluate the expression at x equals 13. Okay, so part C says Max thinks that the square root of operation distributes over the subtraction. In other words, he believes the following equation is an identity. The square root of 25 minus x squared is the same as saying 5 minus x. Show that this is not an identity. Well, it would make sense, right? We could take the square root of 25, which gives us 5, and take the square root of x squared, which would just give me x. But that's not possible. So how I go ahead and identify this, I decide to say, let's pick what x could possibly be, and we can check to see if it is an identity. So what if we let x equal -3? Well, I'm letting x equal -3 because we know what happens in part A. So if I plug in -3, I have the square root of 25 minus -3 squared. So I get the square root of 25 minus 9. And 25 minus 9 is 16, which equals 4. So I know the left side is going to give me 4. 4 should equal 5 minus -3. Well, remember, if the left side is 4 and the right side I had to substitute in -3, 4 equals, remember, 2 negatives make a positive. So I get 5 plus 3 gives me 8. And that's not possible. So it's not an identity. Algebraic expressions can become quite complicated, but if you consider order of operations, notice here it's bold, order of operations and work generally from inside to outside, then you can evaluate any expression for replacement values. So exercise number 5, consider the rather complicated expression. This has a lot going on. It's a fraction, it has absolute values, and it has a square root. Part A says, what operation comes last in this expression? Part B says, evaluate the expression for x equals 2, simplify it completely. So when I think about this, the last thing that I'm probably going to do when I plug x equals 2 into this equation, I may not know. So what if I don't know? Why don't I try doing part B first and seeing what my last step would be? So I have the square root of the absolute value of 2 minus 8 over 5 times 2 squared plus 4. So the square root, 2 minus 8, the absolute value of that is -6 over 5 times the square, 2 squared gives me 4 plus 4. So I have the square root of -6, absolute value is -6, and 5 times 4 is 20 plus 4. Taking the square root again, the absolute value of -6 is +6 over 20 plus 4 gives me 24. Now, can I reduce the square root of 6 over 24? No, because not both of them are perfect squares. However, I can take the square root of 6 over 24 and reduce it as a fraction. So if I do so, I look at 6 over 24 and I realize that both of these could be divided by 6. If I divide both by 6, remember I still have this radical here. The radical of 6 divided by 6 is 1. Over 24 divided by 6 gives me 4. Still not done quite yet. Well, I noticed that 1 and 4 are both perfect squares, so I'm going to rewrite it as the square root of 1 over the square root of 4. Makes me see my perfect squares a little easier. So I take the square root of 1, which is 1, and I take the square root of 4, that gives me 2. So at evaluating this expression where x equals 2, I get 1/2. Well, let's rewind back to part A. It says, what operation comes last in this expression? Well, looking at my answer, the last thing that I did before my answer was I had to take the square root of all of this. So for part A, the square root is last. Okay, exercise 6, I want you to try this on your own. See if you get the answer 1.